Hello there, Mr. Sutton here with the AB Calculus 4-6 Extra Practice Number 1 Solutions on Graphical Analysis. On this problem, we're told that a function f is differentiable and increasing for all real numbers x, and the graph of f has exactly one point of inflection. We want to know which of these is going to be f prime. So we've got a few clues here. One of them is that our function is, well, first off, differentiable, which means that we should have solid lines everywhere, and we do. Next, they said that it's increasing. Well, if f is increasing, that means that f prime is going to be positive everywhere, which means that whichever graph this is, it should be completely above the x-axis. So that's going to eliminate choices B, C, and D. So it's down to A and E. Now, they also told us that there was exactly one point of inflection. Well, that means that f prime is going to have either a min or a max, and only one of them, one turnaround. So we were choosing between A and E. E has two turnarounds here, A has only one, so choice A. On this problem, we're given the graph of f prime, and we want to know what describes the graph of f on this interval. They're just talking about how many relative mins, maxes, and points of inflection we have. So we basically have to go through and find all of those on the graph. All right, so for f prime, if we're changing from positive to negative like we are right here, we've got a relative max for the graph of f. Over here, where we're changing negative to positive, we have a relative min. So that's one of each of those. And then for points of inflection, that's going to be anywhere where f prime is changing direction, and I mean reversing direction. So going from increasing to decreasing or vice versa. So we have a point of inflection right here. We've got one turnaround here. Another one here at 2. And another one down here in this area. So altogether, we have one max, one min, and 3 points of inflection. So that's going to be answer choice A. On this problem, f is a function whose derivative is given by sine of x cubed, and we've got this for an interval. How many points of inflection does our graph have on this interval? This is a calculator question, so if I want to find out points of inflection, and I'm just counting them, I just need to know how many places f prime turns around, goes from increasing to decreasing or vice versa. So I'm going to write f prime changes inc to dec or dec to inc, and let me actually do this on a graph now. So here I am in my y equals. I've just put f prime in as y1, and for my window, I'm using negative to positive 1.8 because that's what they gave me here in the problem. Zoom 0 to get the perfect window on that. And I see that I've got, let's see, 1, 2, 3, 4 different places where we're reversing directions. So that means then that f has 4 points of inflection on this interval. Choice C. On this problem, we're given a graph of f prime for some polynomial, and we want to know which of these statements is true. So the first important thing here is that this is a polynomial. F is a polynomial. That means that all of its derivatives are also polynomials, which means that f and all of its derivatives are continuous and differentiable, which might be helpful as we're trying to prove various things. Okay, so first statement, graph of f is concave up. So that's basically saying that f prime is increasing for the entire interval, and we see here that's clearly not true. We're going from 3 down to 1. Even if this was going up the whole time, we still wouldn't be able to show that we were increasing on the whole interval here because we don't know what's happening in between these values that they gave us. Remember, this is only a couple snapshots of the function. There's a whole world in between, for example, -2 and 0 that we don't know about. Since we can't show, though, that f prime is increasing, we can't show that our graph is concave up. So choice A is out. Choice B, graph of f has at least 2 points of inflection. Okay, well, let's look at that. So points of inflection, those are going to be places where our graph is, our f prime is changing direction. So to get from 3 down to 1 back up to 4, there must have been some direction change happening here. And to get from 4 up to 7 back down to 5, you must have had another change in direction. So f prime is reversing direction on -2 to 3 and also on 3 to 6. I think that's enough evidence to say that yes, we can at least have 2 points of inflection. We might have more, but we've got at least 2. So B is looking pretty good, but let's look at the other ones. C is F is increasing. Well, F is increasing. I mean that implies that all of the F primes in this this function here are going to be positive. And if you look in the table, every F prime is positive that's given in the table. However, like we said before, we don't know what's happening in between our table values. For all we know, our function might dip down below the x-axis somewhere in between -2 and 0 to negative F primes, and then we would have decreasing F values. So we don't know that F prime is positive between our shown values, so this is a no. Next one, F has no critical points. Critical points are going to happen wherever F prime is undefined or 0. We don't have to worry about D and E because we said we have a polynomial, continuous and differentiable, so our derivative is going to be defined everywhere. So it's really just a matter of whether or not F prime takes on a value of 0. And again, they didn't show us that value in the table, but we don't know that there isn't a 0 lurking somewhere in between these table values. Since we don't know that F prime does not equal 0 between these shown values, we therefore cannot conclude D either. And then this last one, F has at least 2 relative extrema. Again, this would require us to have an F prime that was 0, since F prime can't be undefined here. And we just don't know that we have, we can't prove that F prime is 0 somewhere between these table values. It certainly isn't in any of the ones they gave us. So since we don't know that F prime equals or does not equal 0 or is greater than 0 or less than 0 between these values, all these answer choices here are off limits, so choice B is the only one that we can prove. For this problem, we are given the derivative of f, and we want to know at which value of x our f function has a relative max. Well, that's going to happen wherever f prime is going positive to negative. As we look on our graph here, it looks like the only place that happens is here at 4. We're going positive to negative for f prime. So since that's the only place that happens, that's the only place we can say that f has a relative max. So that's going to be choice C. For this problem, we're told we have a twice differentiable function on an interval a to b. F prime is positive, f double prime is negative. Which of these is the graph of the original f function? So f prime positive means our f function is going to be increasing. If f prime is negative, f double prime is negative, that means our original function is going to be concave down. So f double prime negative, concave down. So we're looking for a function that's increasing and concave down. So increasing, that's going to be A, B, or C. D and E are both decreasing. And concave down, that's going to be choice C. For this problem, we have the function f on a graph. We want to know which ordering here is going to be true. So we've got f, f prime, f double prime. We're going to compare them. Let me start with f of 1. F of 1, we're right on the x-axis, so f of 1 has got to be 0. F prime of 1, that's the slope here at x equals 1. They don't have an exact value for us because we don't know the scale of the y-axis, but we're going up, so we at least know that f prime of 1 is positive. And then for f double prime of 1, we are concave down on this interval. So that means that f double prime up there is going to be negative. So if we're trying to put these in order, the negative's got to come first. F double prime of 1. That's going to come before the thing that's 0, so f of 1 is going to be our next thing. And then after that, we've got the positive thing, which is f prime of 1. So we have f double prime less than f of 1 and less than f prime of 1. That's choice D. For this problem, we're given the graph of f double prime, and we want to know the intervals on which our graph of f is concave down. Well, f double prime's sign tells you the concavity of the original, so we just need to know where f double prime is negative. F double prime is going to be negative between -2 and -1, and also between 1 and 3. Therefore, f is concave down on these same intervals. So let's just find those in the answer choice. We've got -2 to -1 and 1 to 3 in answer choice E. For this free response, we're given the graph of f prime, and we're told that we have horizontal tangents at -1, 1, and 3, and they also gave us the area of the bounded regions, but we're not going to need that for this particular problem here. So, part A, find all x coordinates at which f has a relative max. we're looking for places where f prime is changing positive to negative. Looking at our graph, we see that f prime changes positive to negative at x equals -2. Therefore, f has a relative max at x equals -2. And this is what you needed to show to get full justification points. F prime positive to negative. For this part, we want to know on what intervals between -3 and 4 is our graph of f both concave down and decreasing. So concave down means we want f prime to be decreasing. Decreasing for f means we want f prime to be negative. So we're looking for f prime both decreasing and negative. So let's start on the left here and take note as we go. We start off with f prime decreasing but positive, so that interval doesn't work. Then when we get to -2 all the way until -1, we are decreasing and negative. After that, we're increasing. After that, again, we're decreasing. So from -2 to -1 is one interval. From 1 to 3 is the other interval. So we can say, therefore, that since f prime is decreasing and negative on these two intervals, f is concave down and decreasing on those same intervals. For this part, we want x-coordinates of all points of inflection for the graph of f. So those are going to happen wherever f prime is reversing direction. I see that f prime is changing from either increasing to decreasing or decreasing to increasing at x equals -1, at x equals 1, and we're reversing direction again at x equals 3. So therefore, f has points of inflection at all three of those x values.